So today we're going to look at polynomials, functions, and their graphs in a little more detail. So we have this definition. A polynomial in one variable is an expression of the form. Here, I'm going to read it, I'll just let you read it. But here are some important things. The a values are the coefficients. The a values can be any real number. However, the exponents on the variables have to be a non-negative integer. So to be a polynomial in one variable, all the coefficients can be real numbers. You can only have one variable. And the exponents on the variables have to be positive integers only. Alright, so I want to look at this next paragraph. The polynomial is written in standard form when the values of the exponents are in descending order. So you list your largest exponent first, then your next one, and the next one, and so forth. The degree of the polynomial is the greatest exponent. The coefficient of your first term, if it's in standard form, that's called your leading coefficient. So if you look here, here are some examples. Our first one here, we got this expression 12. Okay? It's called a constant. There is no variable. You can think of it having a variable. You can think of it as 12 times x to the 0 power. Because if you remember, x to the 0 power is 1. So this is really 12 times 1, which is just 12. So the degree of this, if it had a variable, the degree of it would be 0. And then the leading coefficient is 12. Alright? Look at the next one. The next one is called a linear. The largest exponent on this is a 1. So the degree of this is 1. The leading coefficient is 4. Because if you notice, all of these are already written in standard form. So if you locate the largest exponent, let's just look at the cubic one. Okay? The largest exponent is 3. The next one is 2, and then 1, and then 0. So the degree of this, since the largest exponent is 3, is degree 3. The leading coefficient is the number in front of that, which is 8. All right, so let's look at this example. Think about these questions as I read them. It says, state the degree and the leading coefficient of each polynomial in one variable. If it's not a polynomial in one variable, explain why. So let's look at A. So first thing we're going to do is we're going to decide, is this a polynomial in one variable? So does it only have one variable? Yes, it only has the variable x. Well, are all the coefficients real numbers? Yes. What about the exponents on your variables? Are all the exponents positive integers? Yes. So this is a polynomial in one variable. And the greatest exponent is 5. So the degree of this polynomial is 5. The leading coefficient will be 8. All right, let's look at B. Is this a polynomial in one variable? No, it's not. Why is it not? Because it has two variables. Because it has a variable x and y. To be a polynomial of one variable, it has to have only that one variable throughout the whole expression. You can't have two different variables like this one does. Okay, what about C? This is a polynomial in one variable, but it's not written in standard form. So let's rewrite it in standard form. So locate the biggest exponent first. The biggest exponent is x to the 8. What's the coefficient on that? -4. I'll write that first. After 8, what's the next biggest one? We have 4. So plus 3x to the 4. After 4, we have 3. We have 6x cubed. And then we got our 2x. So now we have it in standard form. So we can easily identify the degree and the leading coefficient. So this is a polynomial in one variable. The greatest exponent is 8, so the degree is 8. The leading coefficient is -4. All right, so let's take a look at D here. We need to decide, is this a polynomial in one variable? Well, it looks to be one, but it's not. The reason D is not a leading coefficient in one variable is right here. Look where the x is located. The x is located in the denominator of the fraction. So think about when we learned about exponent rules. How can you get a power in the denominator? Well, if I rewrite this as 5x cubed minus 4x squared minus 8x, I can rewrite my last term as 4 times x to the -1. So really, the exponent on this x here, on this variable x here, on my last term, is actually a -1. Remember, when you have a negative exponent, what that does, it moves it down to the bottom part of your fraction and it becomes positive. So, this is not a polynomial in one variable. And the reason is because we have a negative exponent. Remember, all the exponents to be a polynomial in one variable have to be positive. Alright, so here's just some general shapes of different types of graphs that we might see. Okay? Where the graph crosses the x-axis, that's called the root. That's a real root. That's a solution. Okay? That's a real root of that equation. So it says the general shapes of the graphs of several polynomials are shown. The maximum number of times the graph of each function may intersect the x-axis is the same number as the degree of the polynomial. So if you got degree 0, it's not going to cross the x-axis. If you got degree 1, the maximum times it can cross the x-axis is at 1 point. Okay? Over here, a quadratic is degree 2. It crosses the x-axis on this particular example at 2 points. That's the maximum. But it doesn't mean it can't be. That's just the maximum value. It could not pass it at all. Because if we graph this quadratic, okay, it wouldn't pass the x-axis. If we graph this one, it would only cross the x-axis at 1 point. Okay? So this one right here, this example here, has 2 real roots. This example here, it doesn't cross the x-axis, so it has no real roots. And then the last one I did right here, this has just 1 real root. Okay? If you look here at the degree 3 one, what's the maximum amount of real roots that degree 3 can have? 3 of them, because the graph can cross 3. Okay? But it could have less than 3. But the maximum is the degree of it. But when you have a degree 4 equation, the maximum amount of real roots that you can have is 4, but you can have less. Okay? For degree 5, the maximum amount that you can have is 5. You can't have more than 5 if it's degree 5, but you can have less than 5. Now, if you guys remember when we did quadratic equations and we graphed them, we got 2 types of graphs. We got like a U-shaped one, and then we got one that looks like a U upside down. And remember, when it looks like a U upside down, we call this the maximum point. That's the highest point on the graph. And when it opened upward, we call that the minimum point. Okay? And that was for quadratics. Well, now we're going beyond quadratics. We're doing cubics, fourth degrees, fifth degrees, and so forth. So some of your graphs can have multiple maximum points and multiple minimum points. Okay? And it's called a relative maximum and a relative minimum. So if it makes like a valley, like point B does on this graph, we call that a relative minimum. If it makes like a hill, like this, we call that a relative maximum. So I want you to be able to look at the graphs and identify whether it has a relative minimum or relative maximum. And tell me how many. Alright, so one last example. Says, how many real roots does the graph below have? How many relative maximums and relative minimums does the graph have? Okay, so let's answer the first part of this question. How many real roots does this graph have? So how many times does the graph cross the x-axis? Well, this is counting. Crosses here, there, does 1. Crosses here, 2. Crosses here, 3. And here, 4. So this graph here has 4 real roots. Alright, let's see how many relative maximums does this graph have? Well, a maximum is made like a hill shape. How many hills do we have? It looks like we only have 1 right here. So this graph has 1 relative maximum. And now, how many minimums does this graph have? Relative minimums. So those are like the valley ones. Well, we got 1 here, and we got 1 here. So it has 2 relative minimums.